Alright, so let's talk about solutions of a system of differential equations. But before that, remember in chapter 4, we had this type of differential equation, and the solution we can write it like, y c1 e to the x minus x plus xc2 e to the negative x, if you use the auxiliary equation form, right? Okay, so y is the dependent variable, x was the independent variable, and we wrote our solution as a one single function. But now in system of differential equations, you have several dependent variables, right? And we represent all these dependent variables in a vector, right? x1, x2, xn. Now you're solving for dependent variable, right? At the end of the day, you want to solve the differential equation and you want to find what is y is equal to, right? So in this case, what is x1 equal to? What is x2 equal to? What is x3 equal to? So if your dependent variables look like this capital X vector, then your solution should also look like a vector, right? Okay, so let me show you something. Look at this. This is a homogeneous system of differential equation because there's no capital F, right? Plus something. There's no plus vector here, right? Okay, so this is homogeneous. Now they say these are solutions. Look at how the solutions look like. Now don't worry about how I got these solutions. We will discuss that later. There's plenty of time for that. Just for now, think them as they are given to you, okay? Just take them for granted. Now, here's how I define solutions. Solution capital X1 look like, you can see, a vector. 1 a vector times e to the 3t, and this is another solution, okay? So here you have actually two dependent variables because you have two rows, right? Capital X, if you have two rows here in this matrix, that means your capital X have x and y dependent variables, right? Or capital X1, capital X2 dependent variables. So how can you write the general solution in this case? Just like what we did here. Remember, we had two pieces of solutions, right? E to the negative x, e to the negative x. You combine them by a constant. Same idea. So here c1 x1 plus c2 capital X2. So c1 1 e to the 3t, okay, plus c2 negative 1 e to the negative t. So that is how you write a full general solution in a system. I mean, it's the same thing as differential equation. It's just now you're working with vectors, okay? That's the only difference. Your solution will look like a vector. Your variables will look like a vector. Your coefficient is a matrix, right? That's the only difference. Okay. Now here's something cool that they ask in this question. I don't know whether it's cool or not, but okay, anyway. So they say verify that both of them are solutions of this differential equation. Now again, I'm calling this the differential equation, okay, system of differential equation, but it's look like linear algebra, but it is what it is, okay? All right, so how do you verify? How do you verify x1, which is 1 e to the 3t, is a solution of this system, okay? All right, so well, here's what we can do. Let's write this back in form of differential equation. X prime is actually dx1 over dt and dx2 over dt, right? And this side is, well, 1 times x1 plus 2 times x2, right? Here 2 times x1 is equal to plus x2, right? So that is how you can rewrite the differential equation form using the matrix. Try to do that in the other way also. All right, so that's another option. But anyway, how can we prove this is the solution? Well, we can substitute it back to each of this differential equation, right? But that's gonna be painful because you have two differential equations. Now here's what we can do. We can do it in one shot. Let's substitute x. Now to verify something, I mean x plus 5 is 12. We all know x is 7. How do you verify? You just plug x back and show that left hand side and right hand side of the equation are same, right? So let's do it here. So what is x prime given x? Well, x prime from this x is, you have to differentiate that x. Well, differentiate this with respect to time. So this vector can be written as 1 times e to the 3t, it's e to the 3t, 1 times e to the 3t, e to the 3t. I multiply each term of this vector by outside function. I can do that. So let's take the derivative here. Derivative of e to the 3t is 3e to the 3t. Here derivative of e to the 3t is 3e to the 3t. So yes, you can take derivative each row by row in a vector, okay? No problem, you can take them separately. Alright, so that's the left hand side. Let's look at right hand side. Now the right hand side, what you have to do is multiply this matrix by x. What is x? This guy. So e to the 3t, e to the 3t. Okay, so let's multiply. So 1 times e to the 3t, e to the 3t plus 2 times e to the 3t, 2e to the 3t. That's matrix vector multiplication. 2e to the 3t plus 1 times e to the 3t, e to the 3t. Okay, so what do we get? Here 2 plus e to the 2 e to the 3t plus e to the 3t. Here 3e to the 3t. Here also 3e to the 3t. So this is right hand side. Well, left hand side is this. Right hand side is this. Aren't they equal? They are equal, right? Yes. So this is a solution. In fact, yes, x1, capital X1 is a solution. You can do the same for x2 and verify that it's a solution. But the purpose of this video is for you to get used to this matrix vector notation, okay? Think out of those old differential equation that we did before. Now you're working with matrix and vectors, okay? So the takeaway from this video is just our solutions will look like this from now on. They are vectors, okay? And we always write our differential equation in matrix form, okay? All right, you will see more of this later, okay? All right, so I will catch you in those later videos. Thank you very much. Bye bye.